Well, hello guys, here Mr. G with another question. This time is question 3 from the diagnostic exam in 2023 done at the Northern Cape. This question is related to physical properties and organic compound, or physical properties of organic compound. And the question said 4 compounds of comparable molecular mass are used to investigate the effect of functional group on vapor pressure. The results obtained are shown in the table below, and you have different compounds here, and note the following. All those compounds are from different homologous series. And as we're going to do here, we are going to identify the homologous series. The first one, you can see it ends in ane and is going to be an alkane. This is very important. Propan 1 on, you can see that finish in on and is a ketone. Is a ketone. You go to propan 1 ol and then it's N in ol and it's therefore an alcohol. Is an alcohol. And the last one is in oic acid and it will be a carboxylic acid. Okay? Now, because we are working with physical properties, let's write here on the right the type of intermolecular forces that each of them will have. In the case of the butane, we'll have London forces. And there is only. So it's only London forces. Propan 2 on, it have dipole-dipole. Those are dipole-dipole apart from London forces. Propan 1 ol, which is the alcohol, will have hydrogen bond. And then the last one, which is carboxylic acid, will have hydrogen bond but 2 sides. And that is a very important thing here in this part of the question. It has also hydrogen bond, but it has 2 sides for hydrogen bond. Okay, so we have now identified the homologous series of each of them as well as the type of intermolecular forces for each of them. Guys, and you can see there that the intermolecular force is going to be stronger as you move down in these specific trends they gave you there. So here is stronger and here is weakest. Alright, so that is before we go there. Question 3.1, define the term boiling point. So, what is boiling point? It's the temperature at which the vapor pressure equals the atmospheric pressure. Guys, this is a definition you have to learn by heart as it is here. Nothing to say about that one. You do have to learn, and it is a high probability of being asked in the exam. Let's go to question 3.2. Which one of the compounds A, B, C, or D in the table has the highest boiling point? Now, important, you need to know the highest the vapor pressure, the lowest the boiling point. So we're going to write here lowest boiling point. I'm going to write it with BP. I hope you are listening carefully so you don't forget later on what is that. That one have the lowest boiling point, and the one that have the strong intermolecular forces have the higher boiling point. Okay, so saying that, because it's related to the intermolecular forces, you can see the question have the highest boiling point, and that one is going to be ethanoic acid. So in this case, you have to say ethanoic acid or compound D. That one has the highest boiling point. Now they said refer to the vapor pressure. You can say because it has the lowest vapor pressure. Now, weakest intermolecular forces, well guys, we already say that, they don't say explain, in this case is compound A. So compound A, there we go. Question 3.3, refer to the type of intermolecular forces to explain the difference between the vapor pressure of compound A and B. So they're speaking about butane which you know it have London forces only, we already spoke about that, and propan 2-on, which has dipole forces. So we have to explain fully what is happening there. So the first thing you have to say is that compound A is an alkane with London forces only. That is the first important thing you are going to say. You are always going to compare. So you're now going to say that compound B is a ketone. So you say that compound B is a ketone with dipole forces. So this is, let's say, the first thing you have to say all the time, guys. You have to identify the homologous series and tell what type of intermolecular forces each of them has. Then you are going to compare the strength of those two intermolecular forces. So you are going to say that dipole is stronger intermolecular forces than London forces. So you are comparing the strength of the intermolecular forces. That will be the second thing you must say. You can say it with your own words. And then it's coming to the amount of energy needed to break the intermolecular forces there. And then to finish, you'll have to say that one. Less energy is needed to break the intermolecular forces in A than B. And you always have to say or explain this type of work in this specific way. You first identify the type of intermolecular forces, you second compare the strength of the intermolecular forces, and you end up speaking about the energy. Very important. Many learners forget to speak about the energy needed, and this is very important. If you forget, you don't get marks. Now, another important thing, which is be careful. Be careful, do not use the word bonds. If you use the word bonds, you are doomed, guys. You will lose the marks. You can only use the word bonds in the name of hydrogen bond, but you are not breaking bonds, you're breaking intermolecular forces. I hope you are listening carefully, because this one is one of the reasons learners use a lot of marks or lose a lot of marks. Okay, question 3.4. The vapor pressure of compounds C and D are much lower than those of compounds A and B. Name the type of intermolecular forces in A and B. Be careful here, because they want A and B responsible for the difference. Now, what is the intermolecular force? Know the following. All of them will have London forces, okay? But dipole is only in the propan 2-ol. So the one responsible in A and B will be the London force. It's a very good question, that one. It's London forces. London forces. 3.5. Briefly explain the difference in vapor pressure between compound C and compound D. And this one is question 3.5. So they say briefly, but we are going to explain a little bit more. The same as we did here, the first thing we're going to do is to identify and the type of intermolecular forces. So, saying that compound C is an alcohol with hydrogen bond. Compound D is a carboxylic acid with two sides for hydrogen bond, and that is the difference. Carboxylic acid have two sides for hydrogen bonds. Alcohol have one side for hydrogen bond. Okay, that is the difference. So this is the first thing we did. We identify the type of intermolecular force, which is hydrogen bond in each case, but the difference is with the side you can form hydrogen bond. So saying that, then you have to come here and compare the intermolecular forces. The same as we did here. We speak which one is stronger. So the intermolecular forces. So the intermolecular forces in D are stronger than the intermolecular forces in C. And again, we go to the last part. Remember what was? Speaking about energy. So we are going to repeat the same thing. That one is the last one. You can say C needs less energy, or you can say D needs more energy. So we are going to say compound D needs more energy to break the intermolecular forces than C. And that is the final answer for this explanation. Compound D needs more energy. Remember, do not forget the part when you explain about who needs, what compound needs more or less energy to break the intermolecular forces. Be careful as well. Let's make here a note saying that IMF is intermolecular forces. So we're almost done with this question. During a combustion reaction in a closed container of adjustable volume, 8 cubic centimeters of compound A react in excess oxygen. So oxygen is in excess. Alright, and that is an important detail because it means that at the end you will still have some oxygen left in the reaction. According to the following balance equation, there you have the balance equation. If the initial volume of oxygen in the container was 60 cubic centimeters, but remember, this cubic centimeter of oxygen, this one is O2, is in excess. Alright? Is in excess. Calculate the total volume of the gas that are present in the container at the end of the reaction. All the gas in the container are at the same temperature and pressure. Now here is some stoichiometric. Very good. Guys, this 8 centimeter, we started with 8 centimeter cubic of butane. Alright, so now you need to know that 8 centimeter will react with oxygen, but all the 8 centimeter is going to be leaving, is going to end because it is the limiting reagent. So this one is the limiting reagent. So what we have at the end of the reaction, we have all the carbon dioxide, we have all the water, and we have what is left over from oxygen. Remember, you have too much oxygen. So saying that, we can use straightforward, we can use the ratio because all of them are gases and all of them are at the same temperature and pressure. That is called Avogadro's law, you learn in grade 10. So saying that, we are going to use the ratios. First of all, ratios. Okay, and we are going to start with the carbon dioxide. So ratios of the limiting reagent, which is C4 H10 to CO2. This is the first ratio we are going to be working with, and the ratio is 2:8. Remember, the ratios are the numbers at the front. In the case of the carbon dioxide, is 2:8. In other words, 8 cubic centimeters of C4H10, how much of the carbon dioxide will produce? And this one is a cross product here, guys. So you get here that X is equal to 8 times 8 divided by 2. So X is equal to 32 cubic centimeters. It's a centimeter, not decimeters. So that is the first amount we have. Now we know that at the end of the reaction, we have produced 32 cubic centimeters. I want to write decimeters once more. Centimeters of carbon dioxide. Now we are going to repeat the same for the water. So is ratio of C4H10 to H2O. Remember, the ratio is 10:2 in this case. So we write it here, 2 for this one, 10 for the water. So if you have 8 cubic centimeter of the this compound here, how much of the water will you have? You get cross products once more, guys. Then you get that 2x is equal to 8 times 10. So x, this one is simple math, guys. This one will be 40 cubic centimeters. And now we know that at the end of the reaction, we have 40 cubic centimeters of water. All right. Now what we still have to get? The leftovers of oxygen. So we are going to do the ratio again. Let me just try to move all these things a little bit to the left to save space. Let's say there is fine. Okay. So we're going to use the same ratio. Once more, the ratio for, now in this case it's going to be C4H10 to O2, because we need to know how much of the O2 was used up. So we are going to say the ratio here is 2:13. The ratios are the numbers at the front, remember, we just mentioned it. And then if you have 8 of this one, how much of the oxygen will you have? Or let's say, will you need? Once more, cross product here. So this one is 2x equal to 13 times 8. X is equal to 52 cubic centimeters. So what does it mean? 52 is being used, but at the beginning you started with 60. So the question is, how much is left over? Guys, what is left over for oxygen will be 60 minus 52. So that is going to give you 8 cubic centimeters here. Now 8 cubic centimeters is going to be the leftovers in this case. In other words, that amount will still be in the container, is 8 centimeters. Guys, how much gas do we have at the end of the reaction? Well, 8 centimeters plus 32 plus 40. That will give me the total amount of volume left or having at the end of the reaction. So if we do that, we can do it here at this place. The total volume of the gases here will be equal to 8 plus 32 plus 40, and that will give you 80 cubic centimeters. This is the amount of gas at the end of the reaction. And that's it all. Okay, so this is the end of the question at the end of the video. Now, I hope it helped. Remember, guys, the most important thing here is not actually solving the question, because this question may never be asked for you. It was already asked. The idea is to learn how to approach and solve certain questions that could be problematic. But please, if you think it helped, thumb up, write comments, you can suggest, you can ask questions if you want, and I'll see you next time. Next time we're going to go to organic reaction. This is the next question we're going to be solving for this paper. I'll see you next time. Mr. G here.